Right, it should be coming across.
Oh, maybe I need to choose. Yeah. Yeah, now we can see it. I just had to click on something here. Okay, so whenever you're ready.
Right. So thank you so much, everyone. Apologies for not being present over there in person. I really missed that opportunity. Uh, but I'll try to make sure that this work which I'm going to show you today adds up to the value of SECURENET 2026. My name is Vishal Sharma, and I'm a reader in the School of Electronics, Electrical Engineering, and Computer Science. And I'll walk you through one of our projects which we finished last year. That was on the security and resiliency in 3D open networks. And I will present my case from the lens of classical and AI security. So this project was funded by DCIT, and it was a 12 million pound project having around 25 organizations. It was led by University of Surrey, and my role in the project was of security lead. And I was responsible to make sure that the end-to-end components within this project, we call it TUDOR, towards ubiquitous 3D open resilient network, making sure that the ends are tied up in terms of security and what needs to be done moving forward and away if we have to apply Tudor's architecture in modern day networking and upcoming era of, let's say, AI RAN or more towards the 6G journey. I'll be walking you through a couple of things, of course, with the security and performance, followed by the initial architecture we proposed. I do have some list of security challenges and KPIs which we initially identified. Of course, we did not solve everything, so that could be something that can be looked as a takeaway, followed by the security in the context of AI digital twins and mobility management. And of course, then I have two very small concrete security demos to show how security actually worked in the case of Tutor. We all know that security and performance, they don't go very well together. We always look between them as a trade-off. We try to enhance the security of the system while also maintaining the performance. And in that space, sometimes we have to compromise one or the other. In terms of traditional security, we have been looking into the aspects of mutual authentication, all towards integrity and optimized handovers as a part of performance vectors. But in that space, certain things which remain open are very crucial, and those things are listed as our implementation challenges on the right-hand side of your screen. We can have some very sophisticated attacks that can lead from excessive service initiations that can fall into the category of denial of services. You can also have specific denial of services or distributed denial of services attack, but you may also have attacks which are very much prominent to certain and specific sessions like session hijacking. And of course, you can see large scale attacks which can be the resultant of flooding possibilities within your network. Some of the reports which we followed during this entire project, of course, they are the renowned reports. We followed work from 3GPP. We also did follow work from Opener and Alliance, though I have not mentioned it here explicitly, but I do have a couple of works following in the following slides. And some of the technology enablers which we took into account while we were building our solution was based on the principle of network slicing and also exploiting the works in the realms of protocol which are built in the space of EPS, ACA, or EAP ACA Prime or 5G ACA as a backbone while we were trying to initiate protocols for the Tudor project. We also looked into distributed mobility management, and in this space, our critical concerns were about the placement of the security functions. Whenever we have a distributed scenario, we don't know where those security functions would be sitting onto a network. And the reason that the placement of security function becomes critical is that the paths between the devices play a critical role in terms of performance. If you are looking for verifying and validating a device by making your security functions deep into the core, then you are looking at more number of passes to be exchanged between the device and the core, which eventually results into more overheads. So distributed mobility management does bring a lot of concerns in that space. Another important factor in that space is the deregistration of the devices. Once you are in a mobility scenario, and let's say that your device moves from one of your cell to another one, we always look for seamless connectivity that forms part of handover. But a smallest and simplistic thing which is often overlooked, that's deregistration. Once you're moving between the terminals, how you will deregister yourself from the previous one. And often having a weak security measures over here leads to something called replay attacks. And also you would, and if you have to tie it towards a certain security property, you need to ensure that your network is having perfect forward secrecy. We also did a little bit of investigation on identifying new signatures. That was just from the point of view of understanding if the current signatures are weak, whether we need to design new signatures. And if we have to design new signatures, whether we would need to clone the current security functions. And cloning the security function basically means deriving new set of keys from the existing hierarchy. Then, of course, everyone's favorite in terms of buzzword, but not be in terms of performance, distributed ledger technology. We did look into this side of things as well, particularly from the lens of flexible and adaptable security. We were trying to understand if blockchain can be an answer to the application level security, and if it can actually help put traceability back into the networks. We did had both positive and negative results depending how blockchain is actually applied to the ecosystem, particularly for the 3D architecture. And then, of course, in the space of digital twin, some of the concerns for us were when you train your model in a specific network scenario, we are quite confident that you will see number of data drifts across the network because the operation plane is not the same. You will see a lot of heterogeneous scenarios. That means your data will drift. And if your data drifts, you may not be able to have similar performance from your digital twins. And eventually that will affect the type of security you have applied to your system. So these were also going into the background when we're trying to build up our architecture. Like I already mentioned, that key hierarchies are going to play an important role when we talk about security in the network. We used the ones available in 3GPP's draft release 18, and we try to build certain subkeys which we can use for performing different types of security protocols later on. So Tudor's architecture. So Tudor was all about 3D component, and 3D component here is the terrestrial component, your ground networks. Then you have your middle layer, which is more about your aerial networks, your high altitude platform system, or the drones would sit in this layer. And then you will have your space component where you will see your GEO or LEO satellites in that periphery. Specifically, we were concerned about the RIC component from the aspect of Tudor. And like I said, my role was to tie up the security between all these three components. And that made my role quite challenging because we are looking at quite a dense scenario. So if I take Tudor's architecture and if I try to apply it to what's being seen and being available or discussed in literature, or even from the telecoms perspective, we are looking at a very ultra high hyper-connected scenario. And that makes security really difficult. You can say the current protocols may not be able to sustain the pressure. The pressure comes from both the performance side as well as from the vendor's side as well. If you're going to share space between the vendors, you need to run their proprietary protocols as well, and you have to still maintain that the standards are also respected. So that does add a bit of complexity. Uh, Quite often, we also thought about that zero trust might be an answer in that space. We tried to did some experiment. We also validated few ideas, and then eventually we thought that the good answer to this kind of problem may be to disaggregate the scenario. And for disaggregating, we actually looked into the payload. And when I say payload, we specifically looked into the placement of the G node B, our distributed unit, control unit, and then we try to understand if the current security solutions can be applicable to them. The current solutions can be IP tunneling. If you apply IP tunneling, you don't need to worry about end-to-end confidentiality. Of course, the confidentiality of the data at the respective transceivers would be of concern, but at least you can rely on the security of the path itself and you don't have to apply any additional security measures. So that was the thinking going behind for disaggregating the scenarios. In the first case, we tried to put G node B onto the payload where it was positioned on the satellite system itself. And in that space, it was recommended by our finding that IP tunneling, IPsec tunneling should not be used. And the reason was the untrustworthiness of the G node B and its operation, particularly when a service link is formed between the end user and the G node B itself. In the second scenario, when you are looking for placing your radio unit or distributed unit onto the payload, in that case, IPsec tunneling is very efficient because it can work between the control unit and the user plane function because they're of course lying in the periphery of each other. So having an IPsec tunneling over here makes more sense. And similarly, if you are particularly concerned about gnode B and user place function, which is all together onto the payload, in that case, IPsec tunneling is not required at all because you will be having a lot of handovers, and handovers with IPsec could be a bit on tedious side, not easily manageable. We made some critical observations on the integration of the Tudor architecture with the current 3GPP standards as well as the Open RAN Alliance. And then we also look into certain security analysis followed by the aspects of application network and physical layer security. And then we also wrote our first XApp. We also looked into service conflicts and also tried to identify possible scenarios of integrating it with near real-time RIC and non-real-time RIC components. So security challenges, very standard, very rudimentary, very basic security challenges, which still prevail because we somehow live in a world where we don't take security seriously until unless something serious happens. And that means that the security challenges which were applicable 5 years back, they are still applicable now, maybe even on a broader scale. And the impact of these attacks can be huge. We have already seen with some of the recent attacks around the news. Uh, some of the interesting findings were that TLS1 version 1.3 could be an answer to data encryption, and that was like most of the existing systems we see nowadays. They are still uh, using the older version of TLS. Maybe scaling up and moving towards 1.3 can offer higher data encryption standards. We also looked into misbehavior detection and misconfiguration analysis. I'll walk you through each of these individually. I'll skip some of the boring parts in the presentation just to make sure that we are in time as well. We did try to categorize our KPIs, and in that space, we categorized the security requirements based on the type of devices we are encountering. So some of the devices may have an impact on end-to-end security. Some devices may just affect the radio access network and can affect its entire 3D component. So some may only affect the transport component. So some can just be lied into the core of the network, and some can have impact across the entire 3D component, the end-to-end component, as well as the transport component. So we try to look into almost around 12 key security policies, which were categorized across four KPI indices. While we were doing so, an important question which came across for every one of us was how would you define resiliency in the realms of security? Can an answer to security be an answer to resiliency? Are these two terms related? If they are related, how would you ensure that compartmentalization of the network can be performed in the scenario where attack is ongoing? And if you let your network operate to offer resiliency, can you ensure that the attacker may not sweep into the other active parts of the network? So those are some of the critical challenges which we faced. I deliberately brought forward the discussions I was making on the data drift for the digital twin, and these also gets interrelated with the security and resiliency. Uh, we thought that for this kind of situation, building a nice digital twin and running scenarios can be a good answer to understand whether security is to be treated as a term versus resiliency, or whether security has to be treated as term taken together with resiliency. And we don't have an answer yet. It's quite an open question. If you follow UK's report, these are listed as some of the prominent open questions which needs to be accounted for. Uh, Resiliency can be accounted with the help of redundancy, robustness, and recovery, and security all the way looks for more like service monitoring. There is a bit of interplay between them, but if they can sit together or if you can define them in one sentence, it's still an open question. Zero trust architectures may be something which can be explored when we are looking into security and resiliency. In particular, that the policy enforcement points in resiliency can offer you the chance to compartmentalize an active attack. You can actually set policies what happens when certain attacks are met across the network, and zero trust may be an answer to it. It's not fully explored, but it's still something I would say worth exploring. In terms of zero trust, one of the critical things which we are doing as a research group is trying to understand what kind of policy design we need to take into account while we are defining the activities across the policy enforcement point. Uh, this is often an overlooked area. People just believe that there is a policy sitting there which will eventually let operations across the control plane and data plane, but that's not the case. We ran some experiments and we found out that designing efficient policy does play a critical role when it comes to zero trust architecture. Luckily, report 33 from 3GPP is quite enhanced on zero trust, and that can be used to build a case around it. When we look into security policies for and resiliency together from the RIC and non-RIC point of view. Things which actually are tedious and require more investigation is access and understanding of the containers. Real-time um, components are very difficult to manage without containers. RAN intelligent controllers, that's RIC over here, they usually are deployed with the help of Kubernetes. So in-depth, thorough investigation and in access to containers is something which is required to understand the security policies. And when I say access, that should raise an alarm that we are trying to access something which should not be deliberately allowed, but we still need it to understand how the security is defined in the RIC component. You would also need to define KPIs for identifying configurations. And of course, you can write your XApps, which necessarily would operate in near real-time RIC component rather than non-real-time RIC component. The other critical challenge is a lot of the systems we see nowadays, they still use a lot of legacy code. They use common libraries where vulnerabilities might be hiding in their earlier versions, and that may sweep into your current ecosystem. So these are some of the challenges you might see in the space of building your case for security and resiliency. Now, taking on from the security challenges, let's try to understand security in the context of AI. In that space, we thought that the best way to move forward is build a digital twin. Now, this work was done in collaboration with Edinburgh Napier University with Professor Canberg from there. And over here, we focused on building a what-if scenario framework. The what-if scenario framework, what it does, it lets you run multiple scenarios under which your network can be exploited. It, of course, offers you to run analysis on the configurations. You can feed into your network certain types of metrics and understand if the network misbehaves, or you can give the scenario under which your network misbehaved and try to understand what were the metrics which led to such scenario. So that's the utilization of the digital twin which we created as a part of this project. Some of the things which we tried to understand over here was disaggregating the security functions, in particularly when we map the KPIs with the service request of the network. We also use digital twin to understand what components can be digitized and what components should be left at the physical realm. And we also try to understand the adversarial modeling behind the control plane, and of course, using it to build our XApp. Then we moved into something called space of security implications with abusive adversary. Now, these are very interesting types of adversary. Usually, when you evaluate your security of the network, you would define a threat model, you would define an adversary, and what you do, you say, I give my adversary 30% capacity and 30% knowledge of the network, and then you will test your network. But we are living in an era where your adversary may not be limited by those 30 or 40% capacities. You need to test the security of your system at the same level as a traditional user would. So we try to operate this under the name of abusive adversary, where an adversary would have 100% knowledge of your entire network, and its only aim would be to launch as many attacks without considering about its own profit. We try to exploit both the security functions, whether they were sitting in non-real-time RIC or they were sitting in near real-time RIC. We over here used interfaces from both your Open RAN Alliance and 3GPP. The one over here in purple, you can see they are the ones coming from your 3GPP that defines your traditional security function stack. The one in orange are coming from your Open RAN Alliance, which would help linking the near real-time RIC component with the non-real-time RIC component. We ran Markov decision processes based on the network configurations. And what we identified was we asked, so if I have to put it in a very nice summary, the Markov decision processes gave us the strategies under which the network would be more prone to certain attacks. So we were able to identify the settings at which it would be more easier for the adversary to attack it. And that eventually can be used to, in fact, secure your network when you actually hit certain kind of matrix while you are monitoring your entire system. And that's what exactly shown over here, which is like that's where your the attack possibility for given setting would be highest. And that comes out as a combination of fuzzy inferencing operated together with Markov decision processes. Then finally, we moved into the last component where I said that we looked into the mobility management. We looked into a particular scenario where a user is trying to gain access to information from certain drones, which are operated as a part of a public infrastructure, of course, operated by non-terrestrial network gateway. And our idea was how to make this communication secure. And I know that protocol security is something which is more easier to do. So we try to experiment certain protocols which we already have. because our scenario was very much specific, where there is a user who is trying to gain information about certain drone, and then you also have a ground control station who is also trying to access information of drone. So the scenario became quite peculiar, and we had to build a new protocol in this space. One use case I can give you for this kind of scenario is look at your traditional Uber delivery, and now think of your delivery being made by the drones. So if you are a user waiting for a delivery being done by the drone, you will have to understand where your drone is as a user, right? You need to have your ETS, estimated time of arrival, for the drones. At the same time, if you are someone who has initiated those drones as a supplier, you also want to understand what's happening around your drones, where's their location, and what's going on. And the critical challenge is that you both, the user and the supplier, cannot operate on the same privileges. You need to make sure that if you're trying to access information, the information can be basic telemetry. You want to make sure that access control is maintained separately for both the different types of users. And that's where we wrote a new protocol. This protocol is based on chameleon hashing. Um, the advantage of using chameleon hashing is that it can actually help you to work around with collisions, not for the randomness. Usually you would write cryptographic protocols to control the randomness, but chameleon hashing, because of its nature, it allows you to make sure that you can actually do collision resistance for almost any message. And we initiated this as a part of four phases. First was where drone gets registered with the ground control station. That's basically your non-terrestrial gateway coming into play. Drone register itself using a public key. The public key in case of chameleon hashing would be used for hashing, and then the secret key, it's called trapdoor in the case of chameleon hash, and that will be used for collision component. And then user registration phases. User also registers itself with the ground control station. So basically, you can think about both the drone and the user registering themselves with the common server. And then, of course, the comms part happened between the users via GCS towards the drone. And then eventually we did comparisons. So comparisons were based on security properties, where we were able to demonstrate the worthiness of our protocol compared to existing state-of-the-art solutions. And also we tested the cryptographic primitives in that space. Interestingly, this portion over here is very good. Our approach over here took a lot of time because it offered security for certain aspect. For example, it was able to secure against drone capture attack, which is very critical one. Hijacking drone is very prominent, but it was able to secure it against it, but had quite a high operational time. Ours sits somewhere between Evers and Hussein's work, but we do offer more security. One thing we did notice was that our modular exponential calculation were taking more time than scalar multiplication, which was less time, which should be other way around. And that could be the reason of the libraries we were using. We were mostly on the Python libraries. So here is the final bit. So I'm going to show you the security proofs we used, where we used Tamarin to verify the security properties. The first one is about ensuring that the session keys are securely maintained, and they are based on the collision resistance we attained via the chameleon hashes. And then eventually, once these resistance evaluations are done, we also try to test the perfect forward secrecy, which is maintained by the help of a session key between the user and the drone. So because they maintain different session keys, we used these to deregister the drones once they move from one terminal to another, and making sure that if an attacker is trying to inject a message or manipulate the telemetry of the drone, it should not be able to do so. So Tamarin was used for doing the more like formal proofs. And then we also build a proof of concept. Moving ahead. Yeah. So our proof of concept was built using Python. And what we did over here, we created a small scenario where we deployed multiple users who were trying to access multiple drones. And the information they were trying to get was basic telemetry information, the latitude and longitude of the drone. And this was performed using the chameleon hash-based mutual authentication and key agreement protocol. So we tried to induce an adversary into the system, which was, of course, unable to manipulate or inject its own messages. You can see there was not even a single message injected by the adversary, and the telemetry information was securely passed on to the user. So that this covers how a nice security protocol which helps you to perform mutual authentication and key agreement can be converted into proof of concepts. We did publish a lot for this project. Some of these publications are listed over here if you're interested in going more thoroughly into the work I've expressed. Of course, I've touched it in a very light way, but if you read it, please feel free to come back to us with your comments and feedback or for any discussions. Moving ahead, there are a few open challenges. One is, of course, looking into the scalability aspect. When we talk about security, data rates do play a lot of big role. If you're having number of passes and if your data rate is low, then you're looking at slightly higher overheads, which means you might be able to have better security, but you may compromise the performance of the network. Uh, we did not look into context-driven applications because if you're looking into context, the type of security mechanisms would change. This can also go into something called semantic communications. You may need to look thoroughly into what's being passed on the network. Energy sources and choice between the protocols still play quite an important role. This was relative 10 years back. It's still relative now. And two other components is, can we have security by design embedded into the architecture itself? And if so, how would the architecture look like and who would prioritize it? Would it be the telecoms or would it be the standard agencies? And finally, if we really understand AI, where would the human come into play if something bad happens with the AI? So with this, I would like to thank all the research funders who have supported our work, and I will be happy and try my best to answer any questions you may have. Thank you so
Yeah.
much.
Thank you, Vishal. Thank you so much.